All right, welcome to the part 2 of 5.1 video. Just a quick recap. The last video we briefly introduced definition of random variable, discrete random variable, continuous random variable, and also introduced the notation of probability when it comes to discrete random variable. And we kind of did example 2 in the last video as well. Okay, to continue from that, we're going to look at example 3. Suppose we have a fair coin tossed 3 times. So a single coin is tossed 3 times. Let X be denote the total number of heads obtained in the 3 tosses. So the value of the number of heads will land in 3 coin tosses are random. It's determined by chance. And you can get 0 heads, 1 head, 2 heads, or 3 heads out of 3 tosses. So those values are counting values. So in this case here, X is a random variable. So the answer is yes. Okay. And if we were to list all the possible values of X, or the number of heads that obtained from these 3 tosses, we can get 0, 1 head, 2 heads, 3 heads out of 3 tosses. So those are the possible values of the random variable X. List the sample space. Okay, so this is going to be very similar to the given birth situation. 3 children in a family of 3 children. How many possible, outcomes you can have? It's very similar. So with the first coin toss, for this sample space, you can get all 3 heads, right? So H, or all 3 tails. So T. You can get H, T, THT. It should be 8 total. TTH. You can have HHT, HTH. 1, 2, 3, 4, 5, 6, 7. One more. So you can have, let's see, tail first, and then tail first and 2 heads. I think that's the last one we missed in here. So that should be 8 total for this sample space. Okay. Now it's asking to determine the probability of obtaining 2 heads out of 3 tosses. Okay, so how do we do that? Let's see, we can count the outcomes here. So 2 heads out of 3 tosses. So 2 heads out. We know there's 8 total in this case for the total outcomes for the sample space. And then get in exactly 2 heads out of 3 tosses. So exactly 2 heads out of 3 tosses. Those are 3. So the probability in this case is going to be 3/8. And what is 3/8? 3/8 is about 37.5%. Okay, so 0.375 or 37.5%. So that's the chance of getting exactly 2 heads out of. So this is exactly 2 heads. Exactly 2 heads out of 3 tosses. Okay. So now we're gonna try to create a distribution of we're gonna try to create a table which represent the probability distribution of this procedure. So this is the procedure here. Okay, so we're gonna fill in the tables. First, we're gonna fill all the possible value of X. In this case, it's gonna be 0, 1, 2, 3, right? So those are the possible values of obtaining heads that you can obtain. You can get in this procedure. We know that getting exact 2 heads it's going to be 3 out of 8, right? What about all 3 heads? So there's only one scenario there, so that's going to be 1 out of 8. And what about getting exactly 1 head? So let's see. 1 has 1, 2, 3. That's also 3 as well. So you notice that there's a little bit of symmetry in this case here. So, and it's gonna come up later on. So with this table, right, for each X here, for each value of X, we define, or there is a P of X that's associated to each of those values. Okay, so as a matter of fact, that's the first requirement for any procedure that constitute a probability distribution. The first requirement is that for each random variable X, okay, correspond to its probability value. That is, all right, to rewrite this, we'll say for all X, okay, there is P of X. Okay, all right, and the sum of all possible probability values of X must add up equal to 1. Okay, so we say that the sum of all probability of X must equal to 1 for all X. Okay. And then we also learned from the definition of probability value, it must take a value between 0 and 1, include 0 or include 1 as well. So we say that for all x, okay, p of x must be between 0 and 1, inclusive, meaning it can equal to the endpoints. So as long as any procedure that satisfy these three conditions or these three requirements for the probability values of a random variable, then we can put together a distribution, and whether that distribution is a table or graph, we can actually graph this one here. So I'm going to go ahead and just graph this one for you here. Let's see if there's room here somewhere. There's no room. So let's see if we can squeeze that graph somewhere here. So suppose I want to graph that probability distribution. This would be a probability histogram. Okay, so a vertical axis and x-axis. So x-axis could be here, and then here will be p of x. So horizontal x-axis represent the possible values of x. Vertical axis represent the probability with respect to that x. Okay, so we can say zeros here. All right, 1, 2, 3. Right, so we say at 0 we have a probability of 1/8. So you say 1/8, 2/8, 3/8. Okay, 1/8. Okay, so I have 1/8 for the first one, and then at 1 we have 3/8 from 1 to 2, 3/8. Okay. Actually, I think I'm gonna label the horizontal x-axis differently. So I'm going to go ahead and, oops, I'll erase this here. Okay, so I'm going to go ahead and label this one 0, and then 1, 2, 3. So we said at x value equal 1, we have the probability of 1/8, and at x equal to, so 0 will be 1/8, and then 1 will be 3/8. And at 2, we're going to get another 3/8. And at 3, we have 1/8. Right, so that would be the probability, the histogram for this one. Okay. So it looks very, approximately look like a bell-shaped curve. So that will be what it looks like there. So now the next thing we have on the list here is parameters for probability distribution. Okay, so I'm gonna go ahead and erase this here so I can have room. Okay, so parameters, remember, parameters are values such as mean and standard deviation that used for a population, right? Whereas statistics are x bar and s, lowercase s, is being used to describe a sample. So in this case, we have probability distributions are analogous description of a population. Okay, instead of a sample. So the values of the mean and the standard deviation and variance of a probability distribution are considered to be parameters. So for this example here, this tossing coin 3 times. So this table constitutes a probability distribution, and in a sense of a more theoretical approach. So this result here, if we calculate the mean and the standard deviation, this result will be something that can model for all different a fair coin tossed 3 times out there. So right, so you can have a result from tossing coin 3 times, and another person can have another result for tossing coin 3 times. But what we have here is more like a theoretical model that describes what could happen, what will be the average number of heads you can obtain, or the standard deviations. So in a sense of, it's a theoretical model that describe an analogous description of a population rather than a sample. So hence why we have the mean and standard deviations are considered to be parameters. And here are the formulas for the mean of how to calculate the mean, the variance, and the standard deviation for a given probability distribution. The formula looks complicated, but it's not really complicated when you do it. These formula are derived from the arithmetic mean, as we know as the sum of the value of and divided by how many there are. I'm going to show you guys how to do this, just do this example by hand. But for homework or anything beyond this, we are going to use our technology to obtain the mean and the variance and the standard deviation for a given probability distribution. So I start just the first few here, and you can fill in the rest here. So for x equals 0, we first find p of x. So p of x are these values up here, right? So we're just going to fill this in here. So we have the first column, so 18 for x equals 0, 38 for x equals 1, 38 for x equals 2, 18 for x equals 3. And then we're going to multiply x times p of x. So if we times these two together, okay, so we get 0, 38, and then 6, 8, and then 3 8s. And then for the mean, we just sum up all of those. So the mean, it just sum up, you know, x times p of x. So we just take 0 plus 3 8 plus 6 8 plus 3 8, and then that should give us about 3/2 or 1.5. So what this saying that, okay, what this saying this means here, if you were another person that tossed a coin 3 times, we expect that the number of heads that on average you get out of 3 tosses about 1.5 times. Okay, so that's what the mean is referring to, you know, when we look at a probability distribution. So this value here is also known as the expected number. It's the expected value. Okay, what we expect to get if we were to carry out this procedure, you know, over and over again. Okay, now to find the standard deviation is a little more complicated, more hectic, so we have to do this here. So I'm going to fill in the first, I'm actually going to fill out the whole thing. You can do the math yourself. So we do x minus mean, which is 1.5 squared times p of x, in this case is 18, and then you have 1 minus 1.5 squared times 38. You have 2 times 1.5 squared times 38, and then you have 3 minus 1.5 squared times 18, and then compute what this is, and then you take the sum of all those, and then you take the square root of that, and that will be the standard deviation, and that come out to be about 0.87. So what that means is, on average, as you know, randomly we flipping a coin 3 times, the number of heads obtained vary from a person to another person's is on average about 0.87 heads, in terms of, you know, the variation among the number of heads can occur if different people carry out the procedure multiple times. Okay, so that is example 3 and an introduction to probability distribution requirements, and along with the parameters. Those are the mean, variance, standard deviations. I am going to show you how to use this using technology, how to calculate this using technology, so you don't have to do this by hand. To use technologies, you do 1 var. So you do let's see here, enter the data L1, L2, so this would be x and this is p of x, right? And then you just do 1 vars, and then you do 1 var, you know, stats for L1 comma L2, and that should give you the mean and standard deviation. Let's see if we can do that real quick here. Let me open up my calculator here. Let's clear up all the data value in the previous enter. So my L1 will be all the x values, 0, 1, 2, 3. My L2 is going to be the probability for respect to that each of those x values. So 1, 8, 3, 8, 3, 8, 1, 8. Okay, and then I'm going to go ahead and compute the mean and standard deviation. So I'm going to go over to calc, one variable stats, L1, comma L2. So that should give me the mean is 1.5 and the standard deviation is 0.86 in this case. Okay, so pretty straightforward. Okay, All right, so I think I'm gonna stop here on this video, and in the next video, I'm gonna finish up the last part of 5.1.